Good morning, Tensor friends. I got something fun here. It was a homework assignment in one of my books. Determine if the Christoffel symbols given as us are tensors. All right, let's do a little review real fast. Okay, we want to go from a unprimed to a prime, the coordinate, the transpose. So we're going to let r and theta be the unprimed, 1 and 2, and we're going to let the Cartesian x and y be the primed, 1 prime, 2 prime. Okay? Remember the definition of a basis vector. It's given as the partial derivative of a position vector with respect to a coordinate. Now, I want to rewrite that by using the multivariable chain rule to say the partial of that position vector with respect to a prime the coordinate times that prime the coordinate with respect to the unprimed, right? So this is equal to that. So this thing here is given a special name, J I prime I, and we call it the Jacobian. I think it has a specific name, but everybody calls it the Jacobian, so I do too. Now look at this. We have a covariant index here, a free index. So you have to keep these straight when you're doing these transposes. And you see over here, I have the I in the lower, I in the lower. Well, what you're seeing here is the finished result. When I did this on pencil and paper, it's like 4 pages front and back because I got lost like 15 times. These index jugglings can be really, really challenging. Okay, so since we know this, we claim this to be true, right? That the E in the unprimed is equal to the Jacobian in the primed. All right, so let's prove that real quick. So let's choose 1. So I, the free index, is equal to 1. So we got 1 prime 1 times E1 prime and 2 prime 1 times 2 prime. All right, so look at this, an I here and an I here. So we can't change that. When we write down 1, we have to go 1 and 1. Then this is our summation index. So in the first case, it's 1 prime. In the second case, it's 2 prime. So that's how we come up with this expression. And we said that r is equal to 1 and theta is equal to 2, and x is equal to 1 prime and y is equal to 2 prime. So we would write this piece here, j 1 prime 1, as the partial of x, right? That's the prime, with respect to r, which is the 1. And x is given as r cosine theta. The partial with respect to r is cosine the theta. The next one is 2 prime, which is y, and 1 is r. So we got r and y is equal to r sine the theta. With respect to r is sine the theta. So we put that back into this expression and change it back into what we know. So ER is equal to cosine theta EX plus sine theta EY. And we know this is right, right? So that was true. So that means this is a tensor. If this is true, then that is a tensor. That's the point of the exercise. Well, that's just the beginning. This is just a review. Okay. So here's the homework, the question, which was in words, but here it is in symbols. Does the Christoffel the symbol times all of these Jacobians times the Christoffel the symbol primed, are they equal? And now look at this. I've got 3 free indexes, I, J, and K, and I have to follow the rules. So these two are covariant. So I got to have 2 covariants here. One is contravariant. I have 1 contravariant here. And everything else you fill in as primes. Prime, 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 prime. And then everything else becomes the summation indexes, right? The dummy indexes, they call them in tensor the calculus. Okay, so here's the definition of the Christoffel, the symbol that we're going to use. And we can write immediately that this contravariant basis vector, which we know these basis vectors are tensors, so we can immediately write it like this. Now notice that my free index now is in the upper position, so K, K, okay? And then my summation index becomes the primes. And I colored that red so we can go back and find it real quickly. Okay, so now We need to deal with this one. We got that one is easy. We need to deal with this one. So we're going to put in its transpose equation, EI, JI prime I, EI prime back in here. Okay? So we did that. Now we have to use the product rule. So it's the first times derivative of the second. So here's the first. Now the derivative of the second, you do the same trick I did a while ago, is you express it as the multivariable chain rule, right? So it's I prime, the derivative with respect to j prime, and then j prime derivative with respect to j. And we do that because we want to define this as a Jacobian. All right, then it's the second times derivative of the first, which is what that is. All right. So here's what I did. So this derivative of xj prime with respect to xj is the Jacobian j prime j. All right, that's the same thing as this. Now, what's this? Well, you're taking a partial derivative of a partial derivative, and this is the derivative of xi prime with respect to I. That's what this is. And I'm taking the derivative of that with respect to j. All right, so it's a second order derivative. And so I copied this down exactly as it was. And the way you would write this is with the three indexes. So this is I prime, which is in the upper. Then I got two lowers, I and j. So this is saying I'm taking the derivative with respect to the derivative of I prime with respect to I and then with respect to j, or j or I. It doesn't matter. They're interchangeable. But that is the same as this, okay? And then I got to put down my EJ I prime, E I prime, okay? Now, remember, this is where we started. This was the definition of the Christoffel of the symbol. So we got to put this back in for this, and our red thing, this back in for EK. So let's do that. And I want to distribute these with this. So here is this goes in for that. And EK was that we determined above. Okay, so I multiply this times this first term. I pull the scalars out. These are all scalars. And I'm left with this derivative times this basis vector. And now this times this piece is this. And we recognize this as the delta function, the Kronecker delta. Okay, so here's what we got. Now, remember, this is the definition of a Christoffel, the symbol, and you see it right here in the prime, the system. So this is just gamma k prime I prime j prime. Now, if this was a tensor, then this would be all you need to define it from one the system to another, from the prime to the k prime, or invert, from the prime to the unprime. This would be all you need. But that's not all you got. You got all this mess here too. So since you've got an additive term to this, that proves it's not a tensor. So this is what the homework assignment wanted to go through all of this, index Olympics. And the reason they do that is so you can learn how to juggle indexes. That's really the point of the lesson. I think that's what the intention was. So anyway, that was fun. Now let me show you a non-mathematical logic way to prove the exact same thing. What is a tensor? A tensor is a geometric object that is invariant under coordinate change. That means it doesn't change when you change the coordinate. A tensor is a tensor, okay? The Christoffel symbols in the Cartesian, the coordinate frame, they're all zero. All of them are zero because the basis vectors don't change anywhere in the space, so they're all zero. So therefore, if Christoffel symbols are tensors, then they are equal to zero in all coordinate frames. Well, that'd be my conclusion from this, right? If this was a tensor. Well, we know better. The Christoffel symbols in polar coordinates are not equal to zero. They have values. Therefore, the Christoffel symbols are not tensors because this is not true. It's true in one coordinate system, but not the coordinate systems. So it is a variant, not an invariant. All right, wasn't that fun? I'll see you later.